Today I want to talk about limiting reactants. Now, limiting reactants are the reactants that are consumed first in a chemical reaction. And this will determine how much product is possible within that chemical reaction. So to help conceptualize this, I want to talk a little bit about bicycles. So let's say I'm starting about a bicycle company and I have 3 wheels and 3 bicycle frames. Now, if I combine these, I can make 1 bicycle, and I'll also have a couple of frames and a wheel left over. So in this case, even though we have enough frames to make more bicycles, we ran out of wheels. So our wheels are limiting reactant. I can't make any more bicycles unless I'm able to get more wheels. And so since my business is kind of off to a bad start, I go ahead and sell that 1 bicycle, and I use all that money to buy more wheels. I vow that we'll never run out of wheels again. So I buy 5 more wheels. We'll add this to our remainder from our last reaction of 1 wheel and 2 frames. And now I can make 2 bicycles. And now I still have some leftover wheels. And even though I have enough wheels to make another bicycle, I don't have enough frames. So in this case, our frames are our limiting reactant. And this is basically how limiting reactants work. If we run out of one chemical, we cannot go on to have the reaction go forward because we're out of one of those reactants. So I want to go ahead and make a pseudo-chemical reaction out of our bicycles, our bicycle reaction. And so for every 2 wheels and 1 frame, we can make 1 bicycle. And another way of writing this out would be to put a 2 in front of the wheels to serve as our coefficient. This is oftentimes how we do chemical reactions because it takes time to write out chemical reactions and draw the molecules. So a lot of times we'll use coefficients because it's just a lot faster. So to shift this back over into a more chemical-like problem, let's say we have the reaction shown here where we have 2 ammonia plus 3 copper oxide yielding nitrogen gas, 3 coppers, and 3 water molecules. And we're prompted with, we can react 18.1 grams of ammonia with 90.49 grams of copper oxide. How many grams of nitrogen are produced? So with this one, if you ever see 2 quantities given for, say, your reactants or your products, this should cue you in on this is going to be a limiting reagent problem or a limiting reactant problem. And this is very much like how it is in the real world, because normally we will always react 2 sets of things together. And so this is where you can go back and double check to see how much you could get out of this reaction. So to solve this, there's a whole slew of ways that we could go about solving this. The way that I find works best for most people is if you almost treat it like 2 separate problems. So we'll solve it once with just the 18.1 grams of ammonia, and then we'll solve it again with the 90.49 grams of copper oxide. And as you get going, this is actually a really fast process, so it doesn't actually add that much more time over some other methods you can use, and it really helps eliminate a lot of potential mistakes that could occur. So looking at our ammonia, we're going to start off with our 18.1 grams of ammonia, because that's a variable that was given to us. Now we need to figure out some sort of equality that has grams of ammonia in it. And one of our go-tos is always going to be molar mass. So if I figure out the molar mass of ammonia, I'll figure out that we have 17.034 grams of ammonia for every 1 mole of ammonia. And on here, I've indicated where our last significant figure is with a little underline. And this is true for our molar mass as well. Essentially, we're limited here because of the nitrogen only going down to the hundredths decimal place. So we'll continue on. So now we have our 1 mole of ammonia. Since we've gotten to moles of ammonia, we can use our chemical reaction. All right, so for every 2 moles of ammonia, we can make 1 mole of nitrogen. And so I'm going to plug that in here. Again, for every 2 moles of ammonia, that will be equal to 1 mole of N2. So now that we are in our final desired compound of nitrogen, we can apply the molar mass of nitrogen to this, and we say for every 1 mole of nitrogen, we have 28.02 grams of nitrogen. And with this, we get to our final desired unit of grams of nitrogen, and we can just solve for it. So we can multiply the 18.1 grams of ammonia and the 28.02 grams of nitrogen, and then divide by everything on bottom, the 17.034 grams of ammonia and 2 moles of ammonia. So we multiply everything on top, divide by everything on the bottom, and we should get out 14.886775 grams of nitrogen. Now for determining our significant figures, we can see that we have 3 significant figures here, 4 significant figures here. This is an exact equality, so it's not going to limit us at all. And then we have 4 significant figures here. Since this is multiplication and division, we're going to be limited by the one with the least number of sig figs, so the 3 significant figures given in the 18.1 grams of ammonia. So this makes our first 8 our significant figure. So we can go ahead and round that off at this point. So we get 14.9 grams of nitrogen. So we're not done yet because we have only figured it out if ammonia was our limiting reactant. We don't know which is our limiting reactant, ammonia or copper oxide. So I need to do it again, but this time using copper oxide. And so if we start off with copper oxide, the problem was given that we have 90.49 grams of copper oxide. And again, we're going to go to our periodic table and figure out the molar mass of copper oxide. And we come up with 79.55 grams of copper oxide for every 1 mole of copper oxide. Now that we're in moles, we can use our chemical equation again, and we can see for every 3 moles of copper oxide, we'll make 1 mole of N2. So 3 moles of copper oxide for every 1 mole of N2. We'll use our molar mass of N2 again, so 1 mole of N2 for every 28.02 grams of N2. And then we can multiply everything on top, divide by everything on bottom, and we'll be left with units of grams of nitrogen gas. So we'll get 10.62447014 grams of nitrogen gas. And this time our significance is down to the 2 because all the numbers written here have 4 significant figures when we're doing multiplication and division, so we'll be limited to 4 significant figures for our final answer. So we'll get 10.62 grams of N2. Now we need to determine which one is the correct answer. Well, if we stuck with the ammonia, we'd be able to make up to 14.9 grams of N2. If we stuck with the copper oxide, we'd be able to make 10.62 grams of nitrogen gas. So we'll compare the two, and we have to choose whichever one is the least amount because we're going to run out of one of these, so the lesser value is the one that is going to be our real answer. So since 10.62 grams of nitrogen is less than 14.9 grams of nitrogen, we're going to be limited to 10.62 grams of nitrogen for our final answer. And so our limiting reactant is actually the copper oxide. All right, so for this 10.62 grams of nitrogen, what does this really mean? What does it really represent? If I was to react 90.49 grams of copper oxide with an excess amount of ammonia, would I really get out 10.62 grams of nitrogen gas? Well, in theory, yes. This is what is our theoretical yield, and it's the highest conceivable yield for the given amounts of reactants. And so we could potentially get out 10.62 grams of nitrogen gas if we did this reaction. Now the thing is in truth, we probably won't. And so if we were to conduct this experiment, we would get out an actual yield, the amount that you could actually recover during a chemical experiment. And one of the ways that we like to compare these two values of what we actually got out and what we could potentially get out is to look at the percent yield. The percent yield is a ratio between the actual yield compared with the theoretical yield. And we can solve for it using the following equation, where we have the percent yield is the actual yield, or the amount you truly recovered, divided by the theoretical yield, or the amount you could potentially have, multiplied by 100%. So let's say that we were able to do this experiment and we were actually able to collect out 5.31 grams of nitrogen gas. Well, if we did that, we'd set up our amount that we were able to collect in the lab, so 5.31 grams of nitrogen gas, and divide it by our theoretical yield of 10.62 grams of nitrogen gas, multiply it by 100%, and if we do that math, we would get 49.9789 grams, or percent yield for this. Because this number is only 3 significant figures, we're going to be limited to 3 significant figures on our percent yield. And so we'd get a 50% yield, or 50.0% yield. And to be honest, this is actually pretty good. In most experiments, you are not going to get a very high yield. 70% is considered quite good for most synthetic experiments. We can have things that are much lower, and depending on what the reaction is, it might be a pretty good value. You will hardly ever get anything that is really, really close to 100% yield, and in truth, you should never get anything that's above 100% yield, because that means you're creating matter. So whenever doing real lab experiments, 70% yield is normally pretty good, and it's always going to be less than 100% yield. Alright, well, I hope you all learned a lot about limiting reactants, and I hope you have a good day. I'll see you in the next video.